Kevin Walsh, and he is the Samuel T. Fife Endowed Professor of Electrical and Computer Engineering at the University of Louisville. Kevin is the director of the KY Multiscale NNCI site, one of our fellow sites. He has a PhD from the University of Cincinnati, and he also serves as the Associate Dean for the JB Speed School of Engineering at University of Louisville. So Kevin, why don't you start?
All right, thank you. Can you see my slide?
Yes, great.
All right. Thanks. Well, it's an honor to be part of this group and to be given the opportunity to speak a little bit about what our site is all about. So our site is called Kentucky Multiscale. It's kind of short for the NNCI, Multiscale Manufacturing and Nano Integration Node. And the theme of our particular site is converging nanoscale science and science with emerging advanced manufacturing technologies. So this slide gives a bit of an overview of our particular site. Here, I'm going to just go ahead and read this first sentence. So Kentucky Multiscale is a new NNCA site between the University of Louisville and the University of Kentucky that provides users with the unique ability to perform research and build prototypes over various length scales and in a variety of material. We offer core facilities and expertise for traditional microfabrication, MEMS technology, nanotechnology, imaging, and characterization, but with the bonus of as well as varied types of advanced manufacturing processes, such as direct write, roll-to-roll, additive manufacturing, a variety of 3D printing technologies, aerosol jet printing, even some fiber weaving, two-photon lithography, and MEMS microassembly. So we depict this in the image that you see over there on the left. And so one of the strengths of our site is we've been in the area of 3D printing for well over 20 years, partly because of our association with General Electric Appliance Park, and they got into this area for doing prototyping a real long time ago. And we've enjoyed a nice collaboration with them. And so I think the strength of our site is having the expertise and a lot of equipment to do both micro nano as well as functional 3D printing. And that's depicted there in that diagram on the left. So in terms of what we really are, we're a collection of 8 core facilities. We have facilities at both the University of Louisville and University of Kentucky for doing traditional micro nano fab and clean rooms. And then we have imaging facilities at both universities, and the universities are located about 80 miles away. So it makes for a nice collaboration, except on the sports field courts. We have both of them have focus on energy research, and there's a nice dedicated advanced manufacturing facility at University of Kentucky. And then the strength in the additive space here has primarily been at the University of Louisville, and then that lists all the people that are associated with it. So just to talk a little bit about the fab processes, we do have all the traditional kind of deposition, etch, lithography processes that you would typically find in a micro nano facility, including also grayscale lithography and some nice carbon nanotube, some roll-to-roll manufacturing there as well, including some large area carbon nanotube manufacturing capabilities. And then over on the 3D printing additive side, we do span the length scale on that. As I mentioned before, we've got probably 20 different machines for doing your kind of traditional 3D printing, additive manufacturing. And a lot of those are using functional materials. By that, I mean things that you might have your final part, the material you might have your final part made out of, such as titanium or stainless steel and the such. So a lot of those involves a lot of laser processing. But then with some of the new commercial tools out on the market, like aerosol jet printing and two-photon lithography, we do enjoy that area that's kind of converging between the two manufacturing technologies. As well as that, we have a full complement of microscopy, imaging, characterization tools, as well as a lot of stuff needed for the back-end processing and packaging capabilities, as well as then final device testing. So we for our region here, we're one of the few areas where people can come to do kind of one-stop shopping for everything kind of micro nano additive. So then that gives an overview of our site here. We're probably one of the smaller, to be honestly, sites of the 16 site NSF and NCI network, but I think we serve a valuable need in the region where we are located here. So I'll then move on to some of the nano IoT research examples that the different groups have been doing at our NNCI site. So I start off one with it is health related. Here, this was a collaboration between several researchers in the engineering school and researchers in ophthalmology. It was making a device, which you see over there on the right, for monitoring pressure inside the eye for the prevention of glaucoma. This was needed to be an ultra miniature device because it's designed to fit into the anterior chamber that you see there in the middle image of the cross section of the eye. So it needed to be a very small device that would fit in that. It contained a custom ASIC as well as a custom capacitive sensor, all on a Kapton substrate that was machined in the clean room as well, or patterned in the clean room as well as a very fine electroplated coil. It works at 13.56 megahertz, inductively powered. It uses a load modulation strategy, of course, is battery free, and it can be placed either in the anterior chamber, or if a lens is embedded into the middle of it, it could be implanted in the eye when you do a lens replacement there. It has a few centimeter range from an external reader, that would be held up to it to both energize it and take the reading of the pressure. And the group has been doing some bench and rabbit testing. That was kind of generation one. Generation two then was trying to both monitor the pressure in the eye as well as affect the pressure in the eye. Instead of just recording it, trying to maintain the pressure in the eye at an appropriate pressure. And so this contained both the pressure monitor as well as a drainage tube device that would go into the anterior chamber. The advantage of this particular one, of course, besides being able to both control the pressure in the eye, is it's a much less invasive surgery. This device would be placed there along the outside of the eye, and only the drainage tube needed to be embedded into the anterior chamber. And rather than an analog kind of approach to this, by this time, there's a lot of COTS available, RFID chips, miniature chips that have appeared on the markets. And so this Gen 2 device is really a collection of commercially off-the-shelf available devices, including TI's RFID transponder microcontroller and also a COTS piezoresistive pressure sensor. And then it gets interfaced into the Internet of Things using RFID to Bluetooth to cellular to the internet. Okay, that same group is also working on using similar technology, but for monitoring the progress of spinal fusion surgery. So, many times patients will have a degenerative disc or a cracked vertebrae, and they'll have to go in there and place and repair that. And then during that repair process, they'll put hardware in there to address the load of the spine here to carry the load of the spine until the healing process is done. And so there's a need in order to see how that load, to monitor that load, to see when that load eventually is transferred from the hardware that's put into the body back into the repaired spine. And so this uses, again, similar technology right here. This has gone through a couple of different stages of prototyping. Initially, it was a custom MEMS capacitive bending strain sensor here, along with a coil. And this is all then clamped to the device. Prototype 2 was a more digital solution to this, and which required more on the electronic side. And there was also a concern with this that in terms of range, and if you really have an oversized patient right here, by the time this gets implanted, there's concerns whether you had the range. And so there's a tether that gets connected from the actual sensor to the electronics in the antenna. It allows you to have more range. And then over on the right shows the final implementation of this by then a startup company that was developed. This is an example from a group, John Neighbor in electrical engineering. This uses primarily commercially off-the-shelf devices. Application here is for measuring labor contractions in pregnant women for the detection of Braxton Hicks false labor. And this would be worn by the patient here. It's over on the left, you see the printed circuit board, and you see a machined out cantilever in the middle of this, and a metal foil string gauge that is attached. And so this interfaces with the patient right here and monitors contractions and collects that data. And that data then is sent by Bluetooth and then analyzed to determine whether or not the contractions are false or not. The housing was all 3D printed, again, locally at our university. And what was interesting is that they tell me you really need to prototype, even when you're doing 3D printing, you really need your own in-house 3D printers, even though the application for this is going to be small volume, and the final thing will get 3D printed, and you might send that out to get 3D printed. It's always helpful to have your own 3D printers because it's usually a multiple iteration process. Right here, you might design something in the housing and all that, but it's always good to get these things initially, your prototypes 3D printed for your final prototypes that might be manufactured outside. This is a monitor developed by the John Neighbor Research Group, originally for monitoring incontinence here of adult patients. It was originally designed to just interface to these adult briefs that had the conductive ink patterns in them, which would then change, the conductivity would change with as it absorbs moisture. But then they found that, so this would tell you when someone needed to be changed, but they found that there's a lot of other useful information that could be extracted from this. And so the final device actually incorporated a suite of sensors. It was the conductive ink traces in the adult briefs for the moisture content and some COT sensors for temperature, as well as position. And so ultimately it gets used for reduction and detection of urinary tract infections, skin's injury, or even inadequate care. Just briefly, as a professor in bioengineering, just doing some interesting research using sensors and instrumenting rocking chairs here. This is for addressing the spinal cord injury found in children, and the need for them to exercise and go through therapy in order to improve their trunk control. And they found that the rocking motion was something that the small children could do on their own. And they instrumented this chair with a variety of instruments to make it interactive and fun for the young children right here. All that information again sent via the cloud to physicians, and analysis can take a look at the data. Another application here, just focusing on the detector side of it, is a group, the FOO group at University of Louisville, is working on monitoring toxic volatile organic compounds in both indoor and outdoor air. They use a MEMS sensor array here shown on the left. These are 4 different interdigitated electrode structures that get coated with these functionalized gold nanoparticles, and they function as chemi-resistive elements here for monitoring a variety of VOCs. And they claim that it has improved selectivity over your traditional metal oxide devices that need to be heated, and therefore they're also lower power and safer. Okay, just a couple more right here. The Cindy Arnett group is interested in doing wearable electronics, flexible electronics, and sensors. She's especially interested in doing like smart clothing and smart fabrics. And so it's rather interesting. We have an old wooden, or I won't say old, we have a brand new wooden weaving machine here just outside our clean room. And so she's interested in making, smart fabrics. And so she will do some research with our Optimet aerosol jet printing, which is able to print on these fabrics right here, and functionalizing these fabrics with sensors and the such. But she's also interested in figuring out ways, if you want to take kind of traditional MEMS sensors and attach them to the fabrics. And so using strain engineered strategies, she makes these platforms in which they can grip onto the different fabrics of, say, clothing and the such. So that's kind of shown here in terms of a cartoon on the upper right side, and some of the actual devices as they grab hold of fabrics. And then the last one is something that my research group is involved in. And so if you look at the literature, they talk about this trillion sensor vision, that by somewhere around the year 2030, there will be over 1 trillion sensors, which is amazing, out there in the world. Many of those, of course, hooked up to the Internet of Things. And I think this vision also proposes a challenge as well, is many of these sensors will require electrical power and for them to operate. And, the last thing that we need to have to do is go around and replace batteries in all of these sensors. And I realize there's a lot of technology improvements for making things ultra low power, but it would be nice if these sensors either could require exactly no electrical power. So my group is kind of asking the question, can no electrical power smart sensors be developed that autonomously respond to a specific environmental condition or a threshold event? So a lot of times you don't have to be monitoring something continuously, or you may not need to know, for example, if it's temperature, what the temperature is. All you need to know is, did a certain threshold reached? Was there a certain threshold with that in which, like, a food spoils or something, or if I might be looking at like anti-tamper, did it get hit by a radiation source or an X-ray source? And you're just interested in the threshold. So the whole idea is, can you make the device smart enough so once it hits this threshold, your device itself responds? And you don't have to be constantly monitoring the temperature. All you want to know is, did you hit this threshold? And so once it responds, it might mechanically change states. And this is something that you can, you don't have to waste a lot of computing power constantly monitoring these things or applying them to that. And so we developed some technology using some polymer MEMS as well as some other active layers to make these devices that kind of perfectly have these bistable states, these two different states. In this case, these are diaphragms that can either buckle up or buckle down. They're made by a variety of materials. Some materials introduce the strain, other materials are there for mechanical support, and then others are there for active active response to the environment right here. And so this just shows one down here that we have made that responds to a temperature, a certain temperature. So at a certain temperature, these devices will switch states and go from buckled up to buckled down. And so this shows right here how we've been able to design these so that they will switch states at a certain different temperature right here. So by simply changing the diameter of these devices, they will switch states at different temperatures, or by changing the amount of active material that you see in the middle of these, we can get them again to change states from one state to another right there. So I feel like there's a lot of promise in these, what I call kind of event-driven, no electrical power types of sensors, especially for the Internet of Things. If anyone out there is interested in help modeling these devices, this is one area that we could really use some help in, because it's not trivial to figure out how to model these bistable type of devices. So with that, I will end. And thank you for your time. Thanks for everyone participating in this, and thanks for allowing our site to be a part of it.
Kevin, thank you very much. So we have a couple questions in the chat. Can you read them, Kevin? So not everyone can see the chat, so if you could read them out, that'd be great.
Okay, for Mark Allen, let's see, this classification of fab capabilities is great. Maybe we could frame this as what add-ons to our existing traditional capability enable nano IT. That's a good point there. And I do think some of the more the newer technologies, such as the aerosol jet printing, I think our site has found that to be very promising technology, because you can direct write on a variety of topologies. So we can direct write on curved surfaces and the such, and in a variety of materials. In theory, you can put down conductive, semiconducting, and sensing materials down directly onto the surfaces. So I mean, that's one that I think has a lot of promise. And we had another one. What distances are achievable between sensor coil and powering readout for your implantable sensors? So yeah, that I probably did not highlight that. So it's more in the area of, I'm not an expert in this, but a lot of that will depend upon the size of the antenna. So I know for our very small, ultra small device there, it was 2 or 3 centimeters. And then when we were able to go with some of the other devices that either had a tethered antenna or that weren't constrained so much in the space, we're getting more like, several inches for these devices. I think that's all the questions I see.
I think so. Kevin, thank you.